All right, 9 on the dot. Let's get started. Lecture 30. So we're rocking and rolling because I think we only have with the new schedule. I think it's 43 lectures we have. So you can see where we're at. We're definitely through more than half of the semester with not much left to go. So this is week 11. You know, I know that, and so we have 15 weeks. So we're there, and I know for some of you who are going to be walking across the stage in a little bit, those 4 weeks can't go fast enough, am I right? So, okay, how did the ZX homework go? Was that straightforward? Okay, good. This is, I guess today is a slightly unusual day with the homework in that you had 2 homeworks that were due on the same day, but we're going to be on regular schedule for homework for a little bit. I will say that I think it's between homework 6.4 and 6.5 there's a break, so there is one day where I don't give homework because I got to go through the theory and whatnot. But so that's coming soon. So, okay, homework 5.3 is graded though, so I'd say we're up to date on the homework. I'm still a little late on getting the exam graded. The problem is this week is advising central, so between that and registration and whatnot, it's just been sort of a hectic week and whatnot. But like I said, I mean, I definitely am gonna knock it out soon. I just need to sit down and do it when I have the time. Okay, so today what we're gonna do is sort of expand our discussion of beams, and I want to clarify something about what we discussed in the previous lecture and give you a broader picture of what we're talking about with beams. And so I put some stuff here on the board with like columns and beams because I kind of want to draw some analogies between them. Let me go to the slides. Did everybody get the code? Okay, let me go to the slides first and sort of see if I can sort of put this in a broader perspective. But first off, I would say that a fair statement is that the goal of our last lecture were really these 2 terms, which is the term MP and the term ZX. And if you have ZX, MP is really easy because MP just equals Fy times ZX. That's really easy. So, so ZX, I guess, is the real star of the show from the last lecture. And so ZX, I guess by corollary, by MP, sort of represents the theoretical maximum capacity of a beam, okay? So in order to compute the maximum capacity, we would take Fy times Zx. And then how to compute Zx? Well, there's some discussion there. First thing that we did is we differentiated between an elastic neutral axis and a plastic neutral axis. So the elastic neutral axis is what everybody was familiar with before we walked in the door on Monday, and that's where the centroid is located. But the plastic neutral axis is a little different. The plastic neutral axis is where C equals T, or the area on top equals the area on the bottom. And those are not necessarily in the same spot, and we found that out with our lecture last time. And I'll tell you, if you had computed the location of the centroid for the last homework that you all just, you submitted, the one with the plate and then the 2, it was like a big pi symbol, what the girder looked like. Find where the centroid is and compare that to where the P and A is. They're not in the same spot, okay, just point blank. But then once you find the P and A, just area times y, area times y, area times y, sum that up and you'll calculate Z. So I do think that Z is a far more straightforward computation. Okay, everybody with me on that? Okay, now one question that I pose as a result is MP the capacity of a beam? Okay, and my answer to that is, well, it's not that simple. Okay, it's not that simple. For example, in order to illustrate this, let's go back to columns, and I want to make a few statements about columns and see if we can come up with some analogous statements about beams. What is the axial compressive capacity of a column? Well, my answer to that is it depends. All right, it's not that there's no yes or no answer. So for example, if I were to ask you what is the gross section yielding capacity of a tension member, you would say, oh, well, it's 0.9 FYAG, right? Done, right? But with columns, it's not that simple, okay? So what are some statements that we can make? Well, one thing we can say is capacity is a function of slenderness. And I think everybody would agree that's the case, right? Okay. Now, how do we define slenderness? What was our slenderness term for a column? L over R or KL over R, right? So, but basically, yeah. And so one thing I do want to mention, and this is going to seem a little subtle, we really didn't use this term, but just recall that KL over R could also be called LC over R. And remember, LC was that distance between braces, right? An effective distance between braces. And you'll see why I'm throwing that out here, because really the same thing is going to be true for beams, okay? In the case of beams, capacity is a function of LB, okay? And you don't know yet what LB is, but we'll get to that here in a second, okay? Okay. What other statements or conclusions can we make about columns? Well, let's see. Would it be fair to say that as slenderness increases, VPN does what? It goes down, right? Is that a fair statement? Because now that statement is not only reflected by the math, right? I mean, I can go and look at the equations and I can just look and see that as KL over R gets bigger and bigger and bigger, the VPN is going to get smaller and smaller and smaller. That's just the math of it. But is that represented also by the real world aspect of it? Well, true. That's true too. I mean, as a column gets slender and slender and more slender, it's going to get weaker, right? So hopefully that makes sense. So what I'll say is there going to be an analogous statement for beams? The answer is yes, okay? I would say that as this term LB increases, I'll call this phi mn, and I'm going to state it a little differently. I'm going to say it tends to decrease. Okay? And the reason why I'm saying tends to decrease and not actually decrease, I'm going to throw a term out which we'll talk about later. This term CB, which we'll talk about later, it's not going to affect us right now, but I'll say that CB is sort of a weird variable that can change this a little bit. We'll get to that here in a bit. Okay? Okay. So the other thing I want to look at is this. Okay? All right? So I want to look at this. Okay? So on this axis, we'll put LC over R, and on this axis, we'll put Fn. Okay? Now, what do we know about this plot for columns? We know that it looks something like that. Is that a fair statement? The YouTube folks are going to go, what is he talking about? What is he doing on the board? All right, so, okay. All right, so help me out with a couple things. What is this value right there? Fy. Okay? And then there's sort of like this point right there, right? And that point is what? 4.71 square root of E over Fy. And that tells us what type of buckling we're dealing with. Is that a fair statement? Okay, and so I'm going to use the term zone 1. and zone 2. Okay? And zone 1 and zone 2, so this one is inelastic buckling and elastic buckling. Okay? So in other words, columns have sort of two zones of behavior dependent upon where your slenderness falls in comparison to this anchor point right here. Is everybody with me on that? Okay. And is everybody in agreement that this is the maximum capacity? Is everybody okay with that? Okay. So can we sort of conceptualize, without really doing a whole lot of math, what would happen over here? Okay. So this is going to be pretty high level, but we're going to fill in the gaps for this later. Okay. So over here, what I'm going to do is say that capacity in this case is a function of LB. And I haven't talked yet about what LB is, but for the sake of our discussion, LB is going to be the distance between braces, or how slender the beam is. Okay? And as the beam gets more and more slender, it's going to get weaker. Okay? So what I'm going to say is that capacity is going to trend downward. In other words, would you agree that this capacity trends downward, that as the column gets more and more slender, it gets weaker? I'm going to say the same thing with beams. As a beam gets more and more slender, it's going to get weaker too. But I am also going to say that there is going to be a maximum capacity. And what do you think that maximum capacity is? If over here the maximum capacity was Fy, if I'm looking at moments, what's the maximum capacity over here? I'm going to say it's MP. That MP is theoretically the biggest capacity that a beam can withstand. So much so that our curve that we plot is going to sort of be like cut off right here. That I don't care what we calculate, the capacity can't be larger than MP. That we're going to take MP as sort of a, almost like a statutory maximum on what we can expect a beam to be able to provide or supply in terms of capacity. Does that make sense? So, so what I'll say is we don't really know yet what this plot looks like, but what we know is it's going to trend downward. We know the maximum capacity is MP. The other thing I'll tell you is that, and we'll talk about this later, is that there are going to be 3 zones, not 2. But we'll get to that part later. Okay? I'm just right now trying to give you a big picture of what you're going to see throughout the next couple weeks. Okay? Everybody with me so far? Okay. So with that, let's go to the slides now. Okay, so let's talk about the slides. Let's talk about bracing. Okay, so so what I've got here on the slide is sort of like backing up or supporting what I've got here on the board. So to clarify something that I said in the last lecture, and that was what I was getting at, is MP the capacity of a beam? That's not really an accurate way of stating it. The better way of stating it is that for steel beams, the maximum possible capacity is MP. Maybe it's MP, maybe it's not, okay? That's just a beam's maximum possible capacity. What makes things complicated is the fact that beams can buckle, okay? And like columns, beams their beam capacity is a function of bracing. So just to use this board over here, you all know that if I have a column that looks like this, and I put a load on it, this column is going to present different behavior if I stick a brace in the middle, right? Its capacity is going to change. Same thing with beams, right? If you put a brace or more braces on a beam, that's going to affect its capacity. Now the way that we reflect that is through this term LB. LB is how far apart your braces are. So in the case of this, like just to give you kind of an analogy, maybe this term here would be LB, okay? Now, one of the biggest points of confusion when you first start doing beams is that there is a really big difference between how long a beam is and LB, okay? So, but first off, let's just sort of make sure we know what I'm talking about. Okay, so like I said, LB is the distance between braces. What do I mean by braces? Okay, braces are going to be any element that is connecting to the beam such that it prevents the compression flange from moving laterally as it wants to buckle, right? So what happens with beams when you bend a beam, one side's in compression, one side's in tension, and the side that's in tension is going to want to buckle, right? So that's where the stability issue comes from. So if there's something that prevents the top flange or the compression flange from buckling, that's going to be acting as a brace. So for example, here I have, let's say, some steel beams or some steel plate girders that are going to be used in a highway bridge. And we can see, here's the beams. So just for the sake of discussion, let's say these beams are, I don't know, like 120 foot long, okay? The beam might be 120 foot long, but the distance between the braces might only be 20 feet, okay? So in this case, L would be 120 feet, but LB would be 20 feet, okay? Another example of bracing is other beams, right? So if I'm looking at a building, here's this beam that's acting as a girder for supporting floor loads, and you can see that there's beams framing into it. Those beams that are framing into it are preventing this element from moving side to side. So they're going to act as a bracing element for that beam's flexural capacity. Does that make sense? We okay with that? So the notation that I'll use is something like this. So this should be really familiar to everybody. The idea, simply supported beam, uniformly distributed load. But what I have here are these little X's, and these little X's are referring to the braces. And again, I want to be clear that there is a difference between how long the beam is and this LB term. So we might have a beam that's 30 foot long, but only has bracing every 10 feet. So LB would be 10 feet, L would be 30 feet. So where that would affect things is if you're doing structural analysis and drawing a shear diagram or a moment diagram, you're going to use this term for things like computing support reactions, drawing shear diagrams, drawing moment diagrams. The LB terms, you're going to sort of, I don't want to say ignore that, but that doesn't really affect what the shape of the moment diagram looks like. Okay? LB is what you're going to use in terms of capacity. Okay? Now, what do braces do? Well, braces serve to quote unquote strengthen a beam. And what I mean by that is if I have a beam, let's say I have a beam and its LB is like right here, and I throw another brace in where I cut the LB in half, that means the LB is going to be right here, so the capacity is going to sort of trend upward, right? As we start adding braces, the capacity is going to start going this way, right? As long as we recognize we cannot go above this line, okay? The capacity is going to be limited to MP, okay? Is everybody okay with this so far? Okay. Okay, so the first thing that we are going to consider in this class is what's called a continuously braced beam. And what I mean by a continuously braced beam is a beam, let's say like this, so here's a beam, right? A discretely braced beam would be, I don't know, something like that, where there's a defined number of braces, okay? The first thing that we are going to consider, though, is a continuously braced beam. Think about a beam with like an infinite number of braces. So much so that if the beam was continuously braced, we would take LB to be 0, okay? Now, okay, so first question is, would that ever happen in real life? This is a perfect example of it, okay? In this case, we have shear connectors that are acting integrally with a concrete slab or a concrete deck such that the entire length of the compression flange is prevented from moving laterally, okay? Right, so that would be the first example of a continuously braced beam. Another, but just to be clear though, what really getting at when I'm talking about continuously braced beams is I first want to learn how to analyze and design beams where buckling isn't an issue. That's really sort of my point, okay? And if LB is 0, what's our capacity? MP. Okay, so that's sort of the idea for this first section of the class. Okay, our first section of the class on beams. Now, if we're talking about design or analysis and whatnot, we have essentially 3 limit states that we're going to need to assess. Moment, shear, and deflections, right? I mean, you all could probably figure that out from structural analysis last semester. The idea that if I give you a beam, right? I mean, what did we learn how to calculate when we did, you know, when I would give you a beam problem last semester? Here's a beam, we can calculate the reactions and ultimately get the shears and moments on that beam. Those are the internal responses of the beam under those loads. So obviously we would need to provide a beam that's strong enough to resist those responses, right? So shear and moment diagrams are going to feed into our assessment of shear and moment capacity. And then we can also calculate deflections, okay? So a couple things about this. I am actually going to be very loose on my coverage of shear up until the very, very end. And it's going to become pretty clear, maybe even after today, why that's the case. The thing about rolled W shapes in most routine applications is they just have a phenomenal amount of shear capacity. Shear is just not a big issue. In the case of concrete design, that's another story because you have to actually space out your stirrups in order to meet shear demand, and that can be a little bit of a task, right? It's not really going to be a big deal in here, okay? Deflections are also much more straightforward in concrete. So if you take concrete design, you'll know that you have initial deflections and then you have long-term deflections where you have to account for the fact that the beam cracks and there's creep and all this stuff. You don't have to worry about that with steel. It's actually pretty straightforward. So you know what I'm talking about because I know you hate concrete. Okay. All right. So a couple things I want to point you to. The first thing I want to point you to is table 3.2. This is a tabbable page. We're going to be using this pretty much for the rest of the semester. This is table 3.2. You will probably just hear me call this the ZX chart, obviously because of the big old ZX there in the top right corner. But the ZX table is incredibly an incredibly valuable resource. There's a lot of stuff in this that you don't know what they are yet. Things like what is this FEMR? What is this BF term? What are LP and LR? What are all these things? We'll get to that. Don't worry. By the end of this semester, you'll know what each one of those terms are. But there's a lot of stuff packaged into this design aid. This is one of the most useful design aids in the entirety of the steel manual. So much so that this is reprinted in the FE reference handbook as well, the ZX chart. We're going to use this to just look up the shear capacity. Near the end of the semester, we'll look at how to actually compute the shear capacity. But you'll see it's not really going to be that big of a deal. The other thing you'll notice about this chart is that the shapes are sort of packaged into groups, and the top row of those groups are bolded. I wonder why that's the case. We'll get to that later. As for the capacity, though, for a continuously braced beam, we're just going to take phi and P as phi Fy ZX. Okay. Now, a couple clarifying points when we're doing assessment of beams. When we look at moment capacity and shear capacity, those are strength limit states. And what I mean by that is strength limit states, we use factored loads. We use 1.2 dead plus 1.6 live. Service limit states deal with day-to-day performance. And the most common example of service limit states in beam design are deflection limits. Okay? So when we look at deflections, we do not factor the loads. Okay? Because if a beam deflects too much, yeah, that sucks, but it doesn't mean it's going to fall down and kill somebody. Okay? So when we're dealing with fall down and kill people limit states, like strength limit states, we factor the loads. We don't factor them for deflections. So it's a really easy thing to miss. But yeah, we don't factor loads for deflections. Okay. This is the aid that I think is going to make you all pretty angry at me. This is table 3-22. This is the aid where if you look up a simply supported beam with a uniformly distributed load, it kind of just gives you all the formulas. So instead of having to draw the shear diagram, having to draw the moment diagram, it just tells you what the loads are, what the maximum shear, what the maximum moment is, what the maximum deflection is. And so some of you are like, well, why did we have to do all that hullabaloo in structural analysis last semester? So that you respect these. So we'll use these today. But this is table 3-22. This is also tabbable. A couple things I'll mention. Don't forget your unit conversion factors and whatnot. But also, one thing I don't like about this, so for example, if you look at M max is WL squared over 8, and that really doesn't look like an L. So I don't like the fact that it doesn't look like an L. So yeah. Just be careful. Okay. I've done a lot of talking. Let's do some calculations. Okay. So let's look at a continuously braced beam. Okay. And for this continuously braced beam, I want to assess the beam. In other words, I want to assess its ability to withstand the applied moments, its ability to withstand the applied shears, and I want to assess whether it meets a specified deflection limit. The deflection limit that we are going to use is L over 400. Okay? I think you will find this is actually a pretty straightforward enterprise. So we'll sort of dig right in. Before we start chomping away at this problem, though, I'm going to take off my little keyboard here. Before we start chomping away at this problem, I do want to make some statements about the W21 by 62. Okay. Okay. So the first thing I want to look at is the loads. Okay. I want to take a look at this box. Okay. So I have a beam that's 32 foot long, and just so everybody's paying attention, if this is a continuously braced beam and L is 32 feet, what's LB? 0. Okay. Good. All right. So I want to say here, this dead load, see where it says here the dead load shown does not include the self-weight of the beam. What is the self-weight of the beam?
32 times 62.
Okay, all right, all right. So now you're using 62, right? Why are you using 62? Because that's what this number is, right? And what does 62, what does it mean?
It's pounds per foot.
Okay, and this is essentially kips per foot or pounds per foot. So what I'm going to do is I'm going to introduce the term W sub naught, which is 62 pounds per foot, or 0.062 kip per foot. Okay? All right? The other thing I'm going to do is I'm going to ask, what is ZX for a W21 by 62? And we're going to need it later, so I might as well ask, what is IX?
IX is 1,330.
1330?
Yeah.
And that's inches to the fourth. And ZX?
144 inches to the third.
Okay. I've got to believe that at this point, those are pretty easy, straightforward lookups, right? Everybody good with that? Okay. All right, so the first thing that we're going to need to do for this problem is we're going to need to perform some basic structural analysis. Okay? All right, so what I want to start training you on right now is some good habits with this structural analysis. I've been teaching this class for a long time, and this is one of the areas that I have seen students make boo-boos on, okay? All right, so the habit that I want to train you on is I want you to think of the dead loads and the live loads as completely separate problems, okay? Completely separate problems, okay? So let me walk through that, okay? So let's start off with the dead load, Okay, here I'll do it like this. Okay. If I were to turn to table 3-22 in my AISC 16th edition steel construction manual that everybody brought with them to class, right? So everybody brought the steel manual with them. Everybody brought it, didn't they? You suppose? You suppose? All right. So if I were to turn to table 3-22, okay, what case is going to apply to this problem? A simply supported beam subjected to a uniformly distributed load. And by the way, table 3-22, again, I would tab that. That's going to be very useful. It's right before the column section. So there's a series of cases, like case 1, case 2, case 3. Which one's going to apply here? Case 1. And case 1 is the most ubiquitous case we're going to use. So I'll call this okay. Okay. So what I'm going to do for dead load is I'm going to write this down. Would you agree that let's just think of all the dead load that's on the beam. And I propose that all the dead load on the beam is the beam's self-weight plus any weight that is superimposed. Okay? So the self-weight is 62 pounds per foot, but then on top of that, we placed an additional 1,000 pounds per foot, right? That's what's going on up here, right? So this is going to be that. Is that a fair statement? That we have the dead load that was originally applied plus the self-weight of the beam, right? Okay. Now, how long was this beam again?
32 feet.
Okay. Now, from these, I ask you, what is VD and what is MD? So let's start with VD, okay? So let's just think about this. If you have a simply supported beam with a uniformly distributed load, what's the shear diagram look like? It goes up, down, up, right? So the maximum shear is essentially the reactions, right? And what are those reactions? Is that what's in table 322? See? WL over 2, right? A half of the total load. So I'm sort of training you to sort of get a little bit familiar with 322 because you can use it for other load cases, but we'll get to that here in a bit. So this is going to be and what's that going to be? Because everybody brought the Casio FX115ES Plus or similar scientific calculator along with their AISC 16th edition steel construction manual, right?
16.992.
Second.
Okay. Now, what is our maximum moment for a simply supported beam subjected to a uniformly distributed load?
WL squared over 8.
Okay. As a structural engineer, WL squared over 8 is one of those formulas that you'll just sort of remember for the rest of your career. Okay, and so what does that come out to be? $135.936, so we'll say 135.94. And what are the units, by the way? Foot kips. Because that's a moment, right? Second?
Yep.
Okay. Now, live load. What case is going to apply for the live load? It's not a trick question, by the way. I promise. Case 1 as well, right? So WL and L, okay? So the length is also 32 feet. What was the live load?
1.5 kilograms.
So we do the same thing again. And I'm going to go ahead and put, I don't want to say a rush on that, but I think by now you could do this. Bless you. And this is 192. Okay. Now, what do I then do with these values? I would then factor them, right? So I have a dead load, a live load, fair point. Here, let me do this. Could I go ahead and just tell you all what VU and MU equal? Like, is that okay if I just give you the answer? Or so this is 58.8. This is 470.3 foot kips. Okay. Now, before we move on, I want to take a step back and just make sure that everybody's comfortable with what I just did. Is everybody comfortable with that? Yes.
Question. And so the reason you're treating dead loads and live loads completely separate is because they might just be different cases.
That's 100% right. That's
Like
100.
a snow load or something.
Well, no.
Or like something that's like a different case.
Yeah. Okay. So that's exactly what I was going to get at over here. Okay. So like you're 100% right. So some of you are probably thinking, well, wait a minute, Dr. Mike, couldn't we have been lazier by, instead of calculating, let's say, a moment for dead load and a moment for live load and then factoring them, couldn't we have just factored the W's and then done WL squared over 8 to get this answer? And what I would say is that for this problem, that would have worked. But for a multitude of other problems, it won't. And that's why I want you to develop this habit. And a very good example of that is if I were to give you a beam that has this, we'll say WD plus O, but then has a live load that's a point load in the middle, okay? In that world, you would have to treat the dead load and live load separately. And if some of you are thinking, well, here's what I'll do. I'll just take that and convert it to a live load by taking this, dividing it by L, right? Then doing that. If you think this, I want you to stick your hand out and I want you to slap it, okay? Because that is absolutely the incorrect way of doing things, okay? So if you just sort of turn this into a distributed load, you are doing this absolutely incorrectly, okay? And just to give you like a real life explanation, if I was designing this table as a beam, what would be a worse scenario? Spreading the load out or sticking the load all right in the middle? Sticking the load right in the middle, right? And that's what the problem is, right? And so if you spread that load out, you are designing a unsafe beam as a result, okay? So that's no good, okay? So what I'm saying is you would have to treat the, dead load as WL squared over 8, and then you have to treat the live load as a different case, okay? So you have to, that's why I'm really wanting to get you in the habit of treating these separately, okay? Does that make sense? Okay, so now that we've done structural analysis, let's look at capacity. Okay, we're doing good on time. Okay, so for a continuously braced beam, what is phi mn? What did we say it was? Phi mp? Is that what we said? So phi mp, which is what? Phi fy zx? I mean, that's what we discovered in our last lecture, right? So, does anybody remember what phi is for beams? 0.9, 50 KSI. And what was the ZX?
144.
Anybody see a problem we're going to run into with this and this? The units are incorrect, right? So we need to drop a unit conversion in there, because the answer is going to be in inch kips, and I want it in foot kips, right? Okay. So when I chug this out, what do I get? Do I have a second on that? Okay. What conclusion do you make from this? At least just looking at moment. What's that? Well, I'm saying, is it being good? Is it bad? It's good, right? Because here we've got phi mn is 540 foot kips, and we have mu was what, 470.3 foot kips. Okay, so that means that's okay. Okay, remember how we would calculate an efficiency? So another term for an efficiency is a performance ratio. So if you see me write performance ratio, that's what that is. If I divide the two, if I take 470 divided by 540, I get 0.871. Okay? Okay. So is that okay? Me just throwing that out there? It's just that over that. Okay. Now that's moment. I have not yet taught you how to do shear, how to compute shear. So for now, we're just going to look it up. So the purpose also of this example is to get you familiar with table 3.2. So what was our shape again? A W21 by 62. So first off, help me out with this. When you calculate, or let's do this. For a W21 by 62, somebody tell me what this value is listed as. Well, by golly gosh gee. It's like we did something right, isn't it? Because we calculated that. That's actually what's tabulated. So I guess, like, as a future point, a question is, well, can we just look it up? Yeah, you can look it up. I don't have a problem with that. Now, I want you to tell me now what the shear capacity is. The shear capacity is going to be way over on the right. And it's listed as that. 252. So are we good on shear? Yeah. In other words, like we've got So do we have enough shear capacity? Oh yeah, we have quite a lot. In fact, if you calculate your efficiency, you get something like 0.233. Okay? And that, I'm doing this because I want you to see that that's okay. This is a fairly common thing you will see in steel beam design when looking at shear. Okay? Now, if we're looking at plate girder design for bridges, totally different scenario because we're sizing the web plate and we're tailoring it, so we won't get this. But in building design, W shapes for floor beams and buildings, very common that you get a ridiculously low performance ratio for shear. That's okay. Okay. Now, are we missing one? We did moment, we did shear. What did we not do? Deflection. Okay. So let's record some things down. First off, what did the problem say about deflection? Let's scroll that up a little bit. The problem said that the beam has to meet a deflection limit of L/400, but read what it says. The beam meets an L/400 live load deflection limit. So when we assess deflections, we are only looking at the live loads. We will talk about that more on Friday, why we're only looking at the live loads, but it is very common that when you assess deflections like this, you don't consider the dead loads. We'll talk about why next time. Now let's look at E and I. Now I already told you to look up, and we got 1330. What about E? What is E for steel? 29,000 KSI. And remember our live loads, these were case 1. So if I was calculating the maximum live load deflection, how would I calculate that? What's the formula? You would find that in table 322, and table 322 states that the maximum deflection for a simply supported beam subjected to a uniformly distributed load is
5WL to the 4th through 384 EI.
Does everybody see that? Okay, so let's start chugging stuff in. Don't forget your exponent. But before you start chugging things in, anybody see something wrong with what I got here on the screen right now?
Inches to the 4th.
The units are not copacetic, right? On the denominator, we've got KSI in inches, but on the top we have a numerator. I seem to remember in CE 312 that we developed a nice little unit conversion factor that would get our units correct. Wasn't it 1728? Because this on the top is going to be in cubic feet, we need to convert that to cubic inches. And so what do we get for this? So we'll say 0.918 inches. Do I have a second on that? Okay, now what do I compare that against? I know we're running short on time. So I'll call this our limit of L/400. which is 32 feet over 400. I'm going to convert that to inches. And I'm going to go ahead and do this one for you. This one, you get 0.96. So does our beam meet deflection limits? Yes. One thing that's kind of interesting is the performance ratio. It ends up being 0.958. So, which is actually the worst case scenario for this beam? The moments, the shears, or the deflections? The deflections. And that's actually not uncommon in steel beam design. But I guess my question is this beam okay?
Yes.
Beam is adequate. Okay, I know we're like a minute over, my apologies for that. But if you understand that, then I think you'll understand the exercise I cooked up for you this due Friday. I will say that these WL squared over 8, 5WL to the 4th over 384 EI, those analysis formulas are not going to work, so you're going to have to find the cases that apply. But I put that in big old bold text on the homework. But that's all I got, everybody. I will see you all on Friday.